Today we're going to look at factoring quadratics, one of my favorite topics here. Factor trees, and we can remember these from probably elementary school. It's a good example to look at just to begin our discussion here. Of course, our focus is factoring quadratics, but we're going to start our discussion with just what does it mean to factor a number. Here, remember, we look at a number and we say this one's even, so it's divisible by 2. And we say what times 2 equals 48? Well, that would be 24. And then that's also even, 2 times 12. 2 times 6. Of course, 6 is 2 times 3. And when we look at the ends of our trees here, or branches, I should say, those are our prime factors that make up 48. So we can write 48 equals 2 times 2 times 2 times 2, which is 2 to the 4th, times 3. So we have successfully factored 48. Let's also look at a variable example. If we have a to the 3rd, that's going to equal a times a times a. Just an example with some variables there. Okay, the next example we're going to look at is a polynomial. This is a cubic expression, 8x to the 3rd plus 2x. So when we're asked to factor this, we're going to look for things that are common. It's basically backwards distributive property is what I call it here. So we look at the 8 and the 2, and we say what's the biggest number that divides both 8 and 2? Well, that's going to be a 2. So we're going to look at what's common here. In this case, we have a 2 divides both 8 and 2. And then the highest power of x that we can divide out is x to the 1st. So we just say to ourselves, okay, what times 2x would get me back to 8x to the 3rd? Well, of course, that's going to be a 4, and then an x squared. And then what times 2x will get me back to 2x? Well, of course, in this case, it's a 1. So notice what we have here. We have equivalent expressions. Okay, this bottom expression is equivalent to the top expression. We've basically rewritten an addition problem with a multiplication problem. So that's factoring a basic binomial expression there. Okay, the next example I want to look at here is how we multiply binomials, because we're trying to do the opposite of that. We're trying to factor, which is basically division. A lot of times factoring is not taught as division, but that's what it is. But we're going to start with going the other direction, which is multiplication. So just to remind you from Algebra 1, if you remembered using the rectangle, the generic rectangle, or the box, we're going to multiply. And just to keep track of our thoughts here, we could do FOIL, which is first, outer, inner, last, and that's fine. But I like the rectangle because it works for all cases. And it also helps us when we go to factor. So here we're factoring, or we're multiplying, I should say, x plus 3 times x minus 2. So we're starting with a multiplication problem here, and we're going to turn it into an addition problem. So we're going to do x times x, which is x squared, 3 times x, which is 3x, 2 times negative 2, which is negative 6, and we have negative 2 times x, which is negative 2x. Now what we have to do at this point is look and identify, are there any common, or I should say like terms that we can add together? And in this case we do. We have 3x plus negative 2x, which is going to give us 1x. And then we just bring our other pieces over. So we have x squared plus 1x minus 6. Notice again, I'm going to call this an addition problem. And we started with a multiplication problem, because remember, parentheses mean multiplication. Okay, the next piece we're going to look at is now reversing that process. Now notice what I have here. I have the exact same answer down here, and that is on purpose. So I want us to see that when we multiply, the opposite of that is factoring. So when you have just x squared in the beginning, like this example, let me get rid of this for a second. Okay, so let's look at just having x squared plus x minus 6. So when it's just x squared, it's pretty easy because we know that x times x is x squared. So our first terms in both sets of parentheses is x and x. Now we look and ask these two questions. Two numbers that multiply to negative 6 but add to 1x. Remember, if it's just an x, it's a 1x. And two numbers that multiply to negative 6 but add to 1 are going to be positive 3 and negative 2. Because when I multiply 3 times negative 2, I get negative 6. When I add 3 plus negative 2, I get 1. So notice we started with what we ended with what we started with here. So this is a good example of just an x squared. So when it's just x squared, we're just going to use a set of parentheses and lay it out like that. Now our next example, I'm going to need to set up a little grid here for us, a little device so that we can factor, because it does get tougher as we go along. So the pieces that we're going to look at today, I'm going to call ax squared, bx, and c. Ax squared plus bx plus c. So that's how we're going to name our quadratic expressions, our trinomials. We call these trinomials. Now, in order to factor this, we use a little device here called what I call the diamond and the box. And the pieces are very important where they go. So I've laid out a little graphic here. So this applies for any quadratic that that is factorable. So what we're going to do is in the top of the diamond, we're going to do ax squared times c. We're going to bring our bx term here, and we're going to figure out our sides here. Remember, we just looked at an example, two numbers that multiply to -6, but add to 1. That's kind of what we have to do, but it gets pretty complicated when we have something besides a 1x squared. Now over here in the rectangle, once we get our sides, so the spots in the rectangle are going to be our numbers and expressions that we come up with on the sides of the diamond. So those are going to go in our box eventually. And we're just going to, at the last stage, bring in our ax squared and our c into our graphic organizer here. Okay, so that's going to be very important. So make sure you have that in your notes. Okay, now let's look at actual example here. So the example we're going to look at is 6x squared plus 11x plus 3. Now remember, the top of the diamond was ax squared times c. So ax squared times c. So in this case, we get 18x squared. Okay, don't confuse that with the left bottom of the rectangle over here. You're not going to put an ax squared times c. That's a very common mistake. We're actually just going to put the ax squared. So just kind of put that over there for now as a placeholder to remind us. Okay, and in the bottom of the diamond here, we're going to bring in the 11x. So there's our bx term. In this case, it's 11x. Now what we're looking for are factor pairs of ax squared times c, and really just the number part for now will be fine, that multiply to 18, so we can put an m there to remind ourselves, and an a down here, and add to 11. So two numbers that multiply to 18 but add to 11. Now this pair is pretty easy to figure out, but when we get more complicated examples, sometimes it's helpful to have a little table here. So we'll list out all factor pairs of 18. So 1 times 18, 2 times 9, and 3 times 6. And what we're looking for is the pair that adds to the bx number. So in this case, it's going to be 2 and 9. So the sides of the diamond in this case will be 2x and 9x. And we're just going to confirm they multiply to 18x squared and add to 11x. And in this case, that is correct. So we're going to go ahead and put our sides of the diamond over here. And we're going to pull down remember we put our c term up here. Now our last stage, remember our goal here. Our goal is to write factor expression of what we started with. So we want to kind of write what we have down here. In order to get there, once we have our graphic organizer of our rectangle, we need to look for common factors. That's why I started the discussion with factor trees. So we're going to look at our top row up here. The 2 and the 3, the common factor there is a 1. Nothing else will divide 2 and 3 without a remainder. Then we look at our bottom row, 6x squared and 9x, and we say, okay, 6 and 9 is divisible by 3 and also divisible by x. So we're going to factor out a 3x. Then we look at our left column here. We're going to say 2 and 6. The common factor there is a 2. We also have an x in common. And then we're going to look at 3 and 9, our last column over here, which is going to be 3 divides both of those numbers, 3 and 9. Now we have our factor pairs, 3x plus 1, and we have 2x plus 3. Okay, let me circle that. That's our final answer. So all of this mess here comes down to this. So we started with the top here, where it's orange, and we ended down here with factor pairs. Now I just want to state that these two things are equivalent, so they are equal. We've written an addition problem. We've turned that into a multiplication problem. Okay, now we're going to look at a more complicated example here that has a minus in it, so this is going to give us a little more difficulty. It's a good example here. So remember, the top of the diamond is ax squared times c. So in this case, we get negative 54 x squared. The bottom of the diamond now goes as the bx term. So in this case, 25x. And we need numbers that multiply to negative 54 this time, but add to 25. So definitely if we're doing multiplication and the result is a negative number, then we know that one of them is positive and one of them is negative. For now, though, we're just going to write factor pairs of 54. So we're going to look, obviously, we have 1 times 54. We have 2 times 27. We have 9 times 6. And 3 times 18. I think I've got them all there. But we do have our magic pair, that's for sure. So we're going to go ahead and circle that one. So we're looking for two numbers that multiply to negative 54, but add to 25. Since the addition part is positive, that means the bigger number is going to be positive. So when we look at the pair 2 and 27, when I add those two together, if I make the two negative, that's going to make my addition pair equal to 25. When I multiply negative 2 and 27, I get negative 54. So my magic pair is negative 2x and 27x. So I'm going to put those over here in my box. And it really doesn't matter as long as they're on a diagonal. You can reorder this rectangle however you like, but the sides of the diamonds have to be on a diagonal. And so does the ax squared and the c. So remember, we're not going to put ax squared times c over here. We're going to put ax squared. We're going to split them up again, and we're going to put them on a diagonal as well. Okay, we're getting close. We almost have our factor pairs here. So let's go ahead and write down our parentheses at the bottom here to remind ourselves what we're doing here. So we're trying to come up with an equivalent expression to this quadratic at the top that is two binomials. So again, we're going to look at our top row, the 2 at the top, and we have a negative 2 and a negative 18. The common factor there is a negative 2. And notice since that whole top row is negative, that tells me where to place the negative. Now look at my bottom row. 3 and 27 are divisible by 3 and x. My first column here is going to be negative 2 and 3. So I'm going to have a positive 1 and an x. And then 18 and 27, the largest number that divides both of those is 9. So we're going to put a 9 there. So my final answer here is going to be 3x minus 2 and x plus 9. So let's take a look at that for a second. Just make sure that we understand what's going on there. Okay. 3x minus 2 and x plus 9. We've rewritten the top part from an addition problem to a multiplication problem. Whoops, don't need that screen there. Okay, that concludes our video today. Hopefully that helped.